All right, welcome back to the deep dive. Today we're taking a look at a study with quite a title.
Oh, yeah, a bit of a mouthful.
It is. It is. Um, Global Local Analysis of Cost Optimal Onshore Wind Turbine Configurations,
Okay.
considering wind classes and hub heights for all regions of the world.
Wow, they really packed it all in there.
They did. But essentially, this study is trying to figure out the best ways to get electricity from wind power, like the most cost-effective ways.
Makes sense. Onshore wind is a big deal, and it's only getting bigger as we shift to renewables. So, yeah, figuring out how to do it efficiently is super important.
For sure. And this study goes beyond just like, a general overview. It really digs into the details,
Like what?
like different kinds of wind turbines, the ideal heights to install them, and how those factors impact the cost of electricity in all these different locations around the world.
I see, getting really specific. So not just wind is good, but this type of wind turbine is best in this specific place kind of thing.
Exactly. It's all about that level of detail, which is really important when you're trying to, plan for a future powered by renewables.
Yeah.
Like, we need to be smart about it.
Right. It's not a one-size-fits-all situation.
Not at all. And that's actually one of the things this study criticizes about previous research.
Oh, what do they say?
Well, they point out that a lot of the older energy models didn't really account for the latest advancements in wind turbine tech. They were kind of stuck in the past.
Ah, I get it. Things have moved so fast in the renewable energy sector, using old data can really skew the results.
Exactly. And it led to these oversimplifications.
Like what?
Well, like assuming that you could use the same type of turbine and install it at the same height everywhere, which, as we just discussed, doesn't really make sense.
No, not when wind conditions can be so different from one place to another. Coastal areas, mountains, plains, they all have their own unique wind profile.
Right, and those nuances weren't always captured in older models. So this study decided to take a much more in-depth, localized approach.
That's really cool. So how did they go about doing that?
Well, they considered a whole bunch of factors like different wind classes, which we'll explain in a bit, different hub heights for the turbines,
Yeah.
and even stuff like air density and those extreme wind gusts you mentioned.
Gusts, yeah, those can be a real problem. Especially for taller turbines, they can really take a beating.
For sure. And this study even made this assumption about like a buffer zone along coastlines, where they figured those gusts would be even more intense.
I see. So they're really getting granular with the data, trying to account for all those real-world variables.
Exactly. And they even factored in financial data, like projected costs up to 2050, to see how the economics of wind power might change in the future.
That's pretty forward-thinking. So with all that data and this global local approach, what was the big question they were trying to answer?
Essentially, what are the best ways to set up onshore wind turbines globally to get the most bang for our buck, so to speak?
I like that. Bang for our buck.
Hmm.
So how do we make wind power as cost-effective as possible?
Yeah, that's the million-dollar question. And along the way, they're shedding light on the future of wind energy. What role it can play in a world that's increasingly reliant on renewables.
This is fascinating stuff. So walk me through some of their findings. What are the most important things they discovered?
Well, let's start with those limitations of past research that we touched on earlier. The study really goes into detail about why using outdated info and oversimplified models can give you a skewed picture of wind power's potential.
Makes sense. So what were some of the specific issues they highlighted?
Well, one was relying on data about older turbine tech. It's like using a flip phone to understand the capabilities of a smartphone. The tech has advanced so much in recent years that those old models just don't cut it.
Right. So it's not just about how much energy a turbine can generate, but also about things like efficiency, durability, and even the materials used to build them. All of that impacts the cost.
Totally. And they also criticize the tendency to use a single generic turbine type for all locations. Like, imagine using a snow tire in the desert. It's just not the right tool for the job.
Exactly. It's all about finding the right fit for the specific environment.
And that's where this idea of wind classes comes in.
Okay, tell me more about that. What are wind classes?
So the IEC, the International Electrotechnical Commission, they have this standard that classifies turbines into different categories based on the wind conditions they're designed to handle.
Like different levels of windiness.
Yeah, like average wind speeds and the strength of those gusts. Class I turbines are built for the most extreme winds, super sturdy, while Class 4 are for calmer areas.
I see. So choosing the right wind class is kind of like choosing the right tool for the job, depending on how windy the location is.
Absolutely.
Ooh,
And it's not just about performance, it also impacts the cost. Those class high turbines, the heavy-duty ones, they're going to cost more upfront.
that makes sense. Higher upfront cost, but potentially more energy generated in those really windy spots.
Right. And this study really emphasizes the importance of matching the turbine to the local conditions. Like, if you put a Class Y turbine in a Class I wind environment, it might not last very long.
Rah. It'd be like building a house of cards in a hurricane.
Exactly. So wind class is a huge factor in their analysis. Another one is hub height, which is basically how high up the turbine is mounted.
I've noticed that wind turbines seem to be getting taller over the years. Is there a reason for that?
Well, generally speaking, taller towers can capture stronger and more consistent winds, leading to more electricity generation.
So it's like reaching up higher to grab those stronger winds.
Yeah, kind of, but there's a trade-off, as the study points out.
Oh, what's that?
Building taller towers gets expensive. More material, stronger foundations, all of that adds up.
So it's a balancing act between the extra energy you get from higher winds and the cost of getting up there.
Precisely. And this study found that there's often an optimal hub height. Beyond a certain point, the cost of going even taller outweighs the benefits.
Interesting. So it's not just the taller, the better.
Nope. It's all about finding that sweet spot, which this study helps to determine.
Now, what about those extreme wind gusts? How did they factor into the analysis?
This is really where the study gets super granular. They actually incorporated data on extreme wind gusts from global data sets.
Wow. So they're not just looking at average wind speeds, but also considering those sudden bursts of high wind that can really stress a turbine.
Exactly. And those gusts can limit the types of turbines and the maximum hub height that's feasible in certain regions. If the gusts are too strong, it might not be safe or cost-effective to build a really tall tower.
Right. And those gusts are probably more common in certain areas, like coastal regions, right?
That's what they figured. The study even made this assumption about a 100-kilometer buffer zone along coastlines, where they figure the gusts would be even more intense. So within that zone, they excluded certain turbine types that couldn't handle those higher gusts.
That makes sense. It's like they're saying, hey, we know these areas are prone to wild winds, so let's be extra cautious with what we install there.
Precisely. They're factoring in those real-world limitations.
Okay, so they've considered all these factors. How do they actually put it all together to figure out the most cost-effective approach?
Well, the key metric they used is something called levelized cost of electricity, or LCOE.
LCOE. Okay. What is that exactly?
It basically tells you the average cost of generating 1 unit of electricity from a particular wind turbine over its entire lifetime. It takes into account all the costs, the initial investment, the maintenance, everything.
So it's like the total cost of ownership spread out over the years that the turbine is operating.
Exactly. And the goal, of course, is to find the combination of turbine type and hub height that gives you the lowest LCOE.
Makes sense. That's the most economically viable option.
Right. And to calculate the LCOE, they factored in things like the CapEx, the capital expenditure, which is the upfront cost of the turbine and installation.
Right. So that includes the cost of the turbine itself, the tower, the foundation, all that.
Yep. And they also included the OpEx, the operational expenditure, which is like the ongoing cost of maintaining and running the turbine.
Things like repairs, inspections, that kind of stuff.
Exactly. Plus, they use this thing called a capital recovery factor, which accounts for the cost of financing the project over its lifetime.
So they're really looking at the whole picture, from the initial investment to the day-to-day costs of running the turbo.
Absolutely. And they even accounted for how these costs might change over time, using projected figures up to 2050.
Wow, so they're really trying to get a long-term view of the economics.
Yep, it's pretty comprehensive.
Yeah.
And they also looked at this metric called full load hours, or FLH.
Full load hours, what does that tell you?
It basically measures how many hours per year the turbine is operating at its maximum capacity, like churning out as much electricity as it can.
So a higher FLH means the turbine is working more efficiently, generating more electricity overall.
Right. And they found that those Class 3 turbines, the ones designed for moderate wind speeds, often had the highest FLH.
Interesting. So even though those Class 3 turbines might not be built for the most extreme winds, they might actually end up generating more electricity over the course of a year because they're operating at peak performance more often.
Exactly. It's like the tortoise and the hare. The Class 3 turbines are slow and steady, but they win the race in the long run.
Gotcha. So all this sounds very promising, but how do we know that their results are actually accurate? Did they do anything to validate their findings?
They did. They did. They looked at a bunch of locations around the world that are known for having good wind resources.
Hmm.
Places like Patagonia, the UK, parts of the US. And they calculated the LCOE for those specific sites using their model and projected costs.
What did they find?
Well, for a lot of those high wind locations, their model predicted that a wind class 3 turbine installed at a hub height of 120 meters would be the most cost effective.
Interesting. So, not the tallest tower, not the most heavy-duty turbine, but that middle ground seems to be the sweet spot for a lot of places.
Yeah, that seems to be the trend. But there were some exceptions, like in those coastal regions with the higher gusts.
Right, those areas where they had to be more cautious.
Exactly. In those cases, they found that using a Class 1 or 2 turbine at a lower hub height, like around 90 or 100 meters, was often the best option.
So they're confirming that you really need to tailor the approach to the specific location.
For sure. And they also looked at the hourly generation profiles for some of those validation sites. Like how much electricity is being produced hour by hour.
And did those profiles match up with their predictions?
Pretty much, yeah. Like they showed that in Patagonia, a wind class 3 turbine produced a much more consistent and stable output compared to the other classes, which kind of validates their idea that those class 3 turbines are good for places with moderate but consistent winds.
I like it when the data matches up with the theory.
It's always reassuring. And they even compared their results to other studies that had looked at global wind resources, and their findings were pretty much in line with what other researchers had found, which gives them even more confidence in their methodology.
So they've done their homework, they've checked their work, and it all seems to hold up. That's good to hear.
Yeah, they're not just making this stuff up. Now, let's talk about some of the bigger picture implications of this research.
Right. Lay it on me. What are the key takeaways?
Well, one of the most striking things is the global variation in wind resources. Like, some places are just way windier than others.
Yeah, no surprise there. You've got those blustery coastlines and wide open plains, and then you've got areas that are much calmer.
Right. And their study actually maps out those variations in detail, showing the average wind speeds at different heights across the globe. It's pretty cool to see those patterns visually,
So they're giving us a wind map of the world.
basically. And they also show how the cost of electricity from wind varies geographically. Unsurprisingly, the windiest places tend to have the lowest costs, and vice versa.
Makes sense. More wind, more energy, lower cost per unit of electricity.
Exactly. But they also highlight some interesting nuances, like they point out that even though the Tibetan Plateau has really high wind speeds, the air density is so low at that altitude that the wind actually carries less energy.
Oh, right. Air density plays a role too.
Definitely. So it's not just about wind speed, it's about all these interacting factors.
And what about those optimal hub heights? Did they find any global patterns there?
They did. It seems like a hub height of around 120 meters is a good bet for a lot of locations. That seems to be the sweet spot in terms of balancing cost and energy output.
Okay, so not too low, not too high. But did they find any situations where a lower or higher hub height might make more sense?
Yeah, definitely. Like in places with exceptional wind resources, like some parts of Patagonia, they found that a lower hub height, like around 90 meters, could actually be the most cost-effective.
So if the wind is already super strong closer to the ground, you might not need to go as high.
Right. And then, of course, there are those coastal areas with the higher gusts where they recommend using lower hub heights to minimize the risk of damage.
It's all about adapting to the local conditions.
Absolutely. And finally, they looked at which wind classes tend to be the most cost-effective in different parts of the world. And they found that those Class 3 turbines, the ones designed for moderate wind speeds, are often the best choice.
Interesting. So not always going for the most powerful, heavy-duty turbines.
Nope. Those Class 3 turbines are often the workhorses, the ones that can churn out electricity reliably and consistently in a lot of places.
Makes sense. Reliability is key for a stable energy grid.
For sure. But they also found that in places with super strong winds, like Patagonia, those Class high turbines can be more economical. And then in those coastal areas, they often recommend Class 2 turbines as a compromise between performance and durability.
So they're really painting a detailed picture of how to optimize wind power on a global scale.
Yeah, it's like they've created this wind power playbook with different strategies for different environments.
That's super valuable. And they even compared their approach to using a single standard turbine type, right?
They did. They wanted to see how much better their optimized approach was compared to just picking one turbine and using it everywhere.
Like a control group, basically.
Exactly. And they found that using their optimized configurations with different turbine types and hub heights generally led to much higher full load hours, Like in some places, it was a difference of 500 to 800 hours per year.
Wow, that's a significant increase in energy output.
Yeah, it really highlights the benefit of tailoring the approach to the location.
And what about the cost? How did the LCOE compare?
Well, they found that their optimized approach generally resulted in lower LCOE in most regions. Like sometimes it was a difference of 10 to 20 euros per megawatt hour.
So not only are they getting more energy, they're also doing it at a lower cost.
Yeah, it's a win-win. And it really underscores the value of using this more nuanced approach.
So this study is basically saying that we can get more out of wind power if we stop treating it like a one-size-fits-all solution.
Exactly. It's all about understanding the local conditions and choosing the right tools for the job.
Okay, so this research is impressive, but no study is perfect. What were some of the limitations that they acknowledged?
Well, one of the main ones is the spatial resolution of their wind data. Like they're working with data points that cover areas of about 50 kilometers by 50 kilometers.
That's a pretty big chunk of land. Wind conditions can definitely vary within an area that size.
Right. So their model might not be perfectly accurate at capturing those very localized variations.
And they also mentioned the hourly temporal resolution, right?
Yeah, that's another limitation. They're looking at hourly averages of wind speed, which might not capture the full range of fluctuations that can occur within an hour.
So the wind might be stronger or weaker at certain points within that hour, but their data wouldn't necessarily reflect that.
Right. And they also pointed out that their wind speed data was based on a single weather year, 2005. Wind patterns can vary from year to year, so using data from just one year might not be fully representative of the long-term trends.
Makes sense. It's like judging the climate of a place based on the weather on a single day.
Exactly. And then there's the turbine data. They only use data from one manufacturer, Enercon.
So their results might be a bit biased towards that particular brand of turbine?
Potentially, yeah. They acknowledge that using data from a wider range of manufacturers would provide a more complete picture.
And they also mentioned some limitations with the cost calculations, right?
Yeah, they pointed out that they didn't include land costs in their LCOE calculations. And the cost of land can definitely be a factor, especially in densely populated areas.
Right, land scarcity can drive up prices.
For sure. And they also used a uniform weighted average cost of capital, or WACC, globally. But the cost of financing can vary significantly from country to country.
Yeah, different interest rates, different economic conditions, all that.
Exactly. So their cost comparisons might not be perfectly accurate across all regions.
So there's definitely room for improvement, but even with those limitations, this study seems like a significant step forward in our understanding of wind power.
Absolutely.
Yeah.
And they actually offered some suggestions for future research.
Oh, yeah. Like what?
Well, one is to extend this kind of analysis to offshore wind power, wind farms out at sea.
That makes sense. Offshore wind has huge potential, but it also comes with its own unique challenges and costs.
Right. And they also suggested incorporating data from a wider range of turbine manufacturers, as we discussed earlier. Plus, they advocated for more detailed data on how the costs of towers and turbines scale up as you build bigger and taller.
That would definitely make the cost optimizations even more accurate.
For sure. And they also stressed the importance of using the latest climate models to get the most accurate projections of future wind resources.
So they're basically saying, hey, we've made some progress here, but there's still a lot more work to be done.
Exactly. This is just the beginning. And I think that's what's so exciting about this field. There's so much potential for innovation and improvement.
I agree. This study has really opened my eyes to the complexities of wind power and the importance of taking a really nuanced approach to its development.
Me too.
Yeah.
It's not just about sticking turbines in the ground and hoping for the best. It's about understanding the science, the economics, and the local conditions to make sure we're getting the most out of this incredible resource.
Absolutely. So for our listeners out there who want to learn more about this research, where can they go?
Well, the study is titled Global Local Analysis of Cost-Optimal Onshore Wind Turbine Configurations, Considering Wind Classes and Hub Heights for All Regions of the World. And you can find it,
I bet it's online.
oh yeah, you can find it online. Just search for the title, and you should be able to track down the full paper.
Great. And they probably have all sorts of graphs and maps and data tables in there for those who really want to dive deep.
Oh yeah, they really go into detail. It's a fascinating read if you're into that kind of thing.
I'll definitely check it out. Thanks for bringing this study to my attention. And thanks to all our listeners for joining us on this deep dive.
Always a pleasure. And as always, keep exploring, keep learning, and we'll catch you next time on The Deep Dive.